So in our last lecture, let us take a quick revision. So in our last lecture, we understood about what is linear velocity v. This linear velocity v existed even in one-dimensional motion. In circular motion, there was an extra omega, that is the angular velocity. Okay, and the relation between the linear velocity and angular velocity is as follows. That is omega cross r. Agreed. And then we talked about the acceleration. So if there is an acceleration with respect to linear velocity, then there is an acceleration with respect to angular velocity. So there was a linear acceleration and there was an angular acceleration. Now we'll do something interesting mathematically. The mathematical thing that we'll do is, so let us take derivative with respect to time both side. So this side what we'll have? This side we have dv vector by dt, and this side there will be two terms. One is the rate of change of the angular velocity with respect to time. This is the natural thing that we have already studied in our last lecture, which gave birth to angular acceleration. And there is one more interesting term that I want to that I want you to look carefully, that is dr divided by dt. Remember, I have just used the product rule. Now you'd say, hey, what is this? The radius is not changing with time, so it has to be 0. How can you say that dr by, how can you even write dr by dt, since we are considering a circular motion where the radius is not changing with time, so it has to be 0. But this is not the case. This is not the case. Look at this carefully. Even though the magnitude of the radius is constant with time, so if this is the radius, okay, this is r. So when I write r vector, what do I mean by writing r vector? I mean it is made up of some magnitude of r and the r cap. Here the direction of r cap is exactly towards the east. Agreed? When the radius vector, so when the object starts moving along this circle, and when the radius vector reaches here at this position, okay, here also we have a radius vector. But here, no doubt the magnitude of the radius is same, but the r vector, this r vector is actually pointing towards the north. So you see, even though the magnitude is constant with time, the direction of r vector is not constant with time. This quantity gives birth to a new acceleration called as the centripetal acceleration. Okay, what type of acceleration it is? It is a centripetal acceleration, CEN. Okay, now what is the work of this acceleration? So how to represent this acceleration? So let me represent this acceleration as alpha c, and let me write this. This is natural, this is all you know. So this is just an angular acceleration, that is alpha. Okay, so what do we understand from here? We understand that the total acceleration has two things. One is an angular acceleration and another is a centripetal acceleration. We know that whenever there is an acceleration, there is force. It means in a circular motion, the total force is made up of two parts. So first part is your normal force F, and second part is your centripetal force. Okay, so this is something different, but we'll put our main focus in understanding the origin of centripetal force. So from where does this centripetal acceleration arise? Okay, what is the reason behind this centripetal acceleration? Is it and we know whenever there is an acceleration, there is a force. So the force with respect to centripetal acceleration is called centripetal force. So mathematically we got a term that is shouting and saying that there is another kind of force in circular motion called as the centripetal force. Now question is how to intuitively understand what is centripetal force. So consider you have a string, and at the end of the string there is a stone tied to it. Agreed? Have you noticed something? When you try to rotate the stone, okay, each time the stone wants to move in a straight line direction, and you have to put force to keep the stone along a circular path every time. So when your stone reaches this position, the stone wants to fly in this direction. The stone wants to fly in this direction away. But again, you have to put force in your hand to keep the stone along this circular motion. This force that you put on the stone to keep it on the circular motion, have you ever seen that this force is directed towards your hands? Okay, you do one thing, just take a string, tie a stone at the end of the string and rotate it. Each time when you rotate it, you find that you are trying to push the stone towards your hand just to keep it in a circular motion. You'll feel that force. That force is called as the centripetal force. So centripetal force is a logical force. Not only centripetal force comes from pure mathematics. So here the pure mathematics has said that there has to be a centripetal force, but also you experience the centripetal force in your day-to-day life. When you try to rotate an object around a circle, you have to put force towards the center to keep it on a circle. If there is no centripetal force, then this stone will not move in a circle. The moment you cut the rope, what happens? The moment you cut the rope, the stone will fly in straight direction. Okay, the moment you cut the rope, the stone will fly in the straight direction. So stone always have a tendency to move in a straight direction and fly in a straight line. But what you do is you keep the stone in a circular path by pushing the stone always towards the center. This push that you have to give is called as the centripetal force. And because of this centripetal force that you are always giving to the stone, because of this, the stone goes on moving around a circle. If there were no force like this, you would not have been able to keep the stone in the circular path. This is the origin of centripetal force, and this type of force has no analog in the translational motion. So in one-dimensional motion, you only knew force, but here you not only knew a force that can act along along this circle, okay, but there is another force that acts along the center, and that force is a new in circular motion called as the centripetal force. So now that we have learned centripetal force, let me tell you one thing. You might have seen the stone always have a tendency not only to move forward. This forward moving tendency of the stone comes from kinematics. But you always feel that the stone has a force acting along this side. This is called as the centrifugal force. Because of this centrifugal force, you have to put a centripetal force that balances each other. Agreed? For example, if you have ever sat in a bus, okay, so consider you are sitting in a bus and the bus, consider, takes a turn. When it comes to an edge, the bus takes a turn. The moment the bus takes a turn, you feel as if you are being pushed along this direction. Okay, when the bus is here, when the bus is taking the turn, you feel a pushing force along this direction. This pushing force is called as the centripetal force. This is same as the centrifugal force. If you are tied to a center, then there is a centripetal force that balances the centrifugal force. In a bus, you are not tied to anything. You are free and you are rotating. When you are free and you are rotating, you experience something called as the centrifugal force, and this is also a consequence of the circular motion. Agreed? In the next lecture, I will prove an expression that the centrifugal force F is proportional to the velocity square and inversely proportional to your radius. I mean, if you make a stone rotate faster, so if you make the stone, consider initially you make the stone rotate at a velocity 5 meters per second, you will feel that the centripetal force that you have to give is less. Now you make the stone rotate in circular motion at 100 meters per second. Now you will feel that you have to put a strong centripetal force towards the center, just because you need to keep the stone in the circle. So obviously one thing is sure, that the centripetal force depends on the velocity with which you are rotating the stone. An interesting thing about the centripetal force is that it is inversely proportional to the radius of the circle along which you are moving the stone. So we'll discuss more in our next lecture about this.